Perfect. All right, so today's talk, I'll talk about a few line work that we have done in our group on solving inverse problems. So an inverse problem is one when you have some measurements y of something, of some object x that's been shown in this arrow on top. But the measurement process is noisy and lossy. So the inverse problem is ill-posed. And the goal is to infer x and perhaps even the entire distribution p of x given y. Since it's ill-posed, one common way to solve these kinds of problems is to take a Bayesian approach. So here you put down a prior over the data x and try to minimize the reconstruction error. So one of the challenges in these kinds of problems is often p of x may be hard to learn because perhaps we don't have data. We don't have observations of x itself, so we cannot easily learn p of x. And of course, the optimization could be hard to solve, so all of this may be intractable. So in today's talk, I'll talk about three problems where we're going to reimagine this equation in different ways in order to solve these kinds of problems efficiently. And our goal is going to be reuse bits and pieces of automatic differentiation and graphics pipelines and differentiable renderers and so on to model everything in sort of deep learning packages. So in all of these problems, we don't have access to x directly, so we can't train the inverse problem or the inverse model p of y given x using supervised learning, and instead we'll use sort of learning-free approaches. So in the first part of the talk, I'll talk about a problem where p of x is implicit. So we'd like to reconstruct some signal given multiple measurements. In the second part of the talk, we'll try to discover p of x. So given a large number of images, we'd like to discover what's the latent space of 3D objects that could have created these images. And in the third part, I'll talk about a problem where x is a program. So x transformation x to y is obtained using a rendering engine or a compiler that takes the program and generates a 3D shape or a 2D shape. Okay, so let's start with the first one. In the first part, we'll assume t is parameterized using something. So perhaps it's parameterized by viewpoint. And what you have are multiple observations or multiple measurements of the same instance x through different viewpoints. Okay, so this is, for example, you might have multiple views of this teapot from or different measurements in tomography coming from different angles of your X-rays and so on. So one interesting observation made 2 years ago was this idea that you can replace this energy minimization problem with an unconstrained optimization problem as follows. So instead of minimizing x directly, you reparameterize x using a generator. So x is some parameterized function, f theta of some input noise. And instead of optimizing x, you optimize the parameters of this neural network. And it turns out that because of the way these deep networks work, even random parameters generate smooth functions. And in fact, if you replace this p of x by the space of outputs that a neural network can generate, you induce a reasonable prior over natural images. So that was the idea in this deep image prior paper by Ulyanov et al. And you can think of why this works by thinking of this a random neural network as a Gaussian process, and similar observations have been made by other people as well. But the main advantage is that now you can replace p of x using a parameterized neural network family, and the optimization can becomes easy to solve. But that can only be done if the function t is also differentiable because we would like to backpropagate through the error function. So it turns out that there are lots of scenarios, especially for shape reconstruction, where t indeed is differentiable. So let's look at tomography, for example. So given an image, the way tomography is computed is mathematically, what you compute is the Radon transformation. So these are essentially line integrals of the function, which is shown as this function r, which is parameterized by the slope and intercept of the line. So the transformation, forward transformation, can be easily implemented using upsampling and integration in let's say, PyTorch. And this becomes a differentiable module that you can backpropagate through. So you can so replace that energy minimization problem by composing this deep image prior with this differentiable projection function and solve this using gradient descent. Okay. All right, so let's see how this works as a comparison. These are 3 images, and these sinograms or these radon projections were computed with sparse set of angles, and there was also a little bit of noise. So once you do a very naive inversion, this is filtered back projection, which has a very sort of poor prior over the X, you get the reconstructions that look like this. So you, on the top are 2 numbers, PSNR and SSIM, both need to be higher for good reconstruction. So with the better prior, this is TV prior, the reconstructions look better. This is iterative BM3D. This is one of the top performing methods for denoising. The reconstructions look quite a bit better, but combining this deep image prior together with the differentiable radon projections, you get quite a bit better results. Okay. So again, these methods are trained without any label data, so you didn't have access to what clean samples look like, and they're optimized from scratch on each example. So the same idea works exactly the same way, roughly, for reconstructing 3D shape from a bunch of silhouette images. Okay, so this is the classic problem of visual hull reconstruction, and a baseline algorithm is to simply intersect the volumes. Okay, but that process of a volume to silhouette is again very similar to these line integrals, and you can combine that with these noisy observations to reconstruct the 3D volume itself. So here, instead of generating an image, we're generating a implicit function in a volumetric representation, similar to what Pascal was describing earlier, where we're representing the shape itself using a neural network. Okay, so here are some examples. So compared to space carving, our results tend to look smoother and also works for sort of more complex shapes. But one of the main advantages is our method is quite a bit more robust to viewpoint noise. So if you have errors in viewpoint estimation in these visual hull algorithms, you tend to lose all the details in thin structures. So for example, the table legs are gone because the viewpoints cancel each other out. But because our rendering process is differentiable both with respect to the shape and the viewpoint parameters, we can optimize all of this jointly to do the reconstruction. Okay. So similarly, you can write down a render that computes the depth of an image instead of a binary silhouette. These are equations which are simply computing visibility of each pixel and then adding up the visibility to compute the depth. Okay. So now you can reconstruct the 3D shape given noisy depth images, and these are what the constructions look like. And even with quite a bit of noise and sparse set of inputs, you can get reasonable reconstructions of 3D shapes. Okay. So now look at a harder setting. So imagine you have a collection of images. So you open up a catalog of furniture and you find all these chairs, and each chair is perhaps taken from a different viewpoint, and they're all different. And in your head, you would like to imagine what is the space of shapes of chairs that could have generated these images. Okay, so if you did not have viewpoint annotations and there weren't the same instance, it rules out some algorithms that you can imagine. So visual hull in the previous slide wouldn't work, structure from motion wouldn't work, and this becomes much more challenging. Okay. So the motivation here is like, you can go to the internet and find pictures of things you're interested about, so puffins, and you would like to understand what is the 3D shape distribution of puffins. And you can see these puffins are all different, they're articulated, they're taken from different viewpoints, and ideally would like to do this without having to label lots of things in each image. Okay. So this problem is also what's called non-rigid structure from motion. And the reason this is hard is often you may not have a sense of what the shape distribution looks like. So much of non-rigid structure from motion has been applied for objects where you have a compact 3D shape representations of perhaps faces and human bodies, but if the object is unstructured like a chair or is heavily articulated, then discovering the 3D shape itself is, or representing it is challenging. So we use the power of deep networks to represent the latent space of 3D to model the P of X itself. Okay, the problem setting is you're given a set of images. So again, we'll simplify this problem. Again, it's a toy problem where we assume we have a bunch of silhouettes. So you are given a bunch of projections of airplanes here. And your goal is to discover a 3D shape distribution of airplane shapes. The way we're going to do this is we'll generate a factorized method to generate images. First, we will generate 3D shapes and then project them onto binary silhouettes using a differentiable render. Okay, so here G theta Z is a sampled shape from the generative model, and PR of that is its projection. So the idea is if I sample enough of these, I get a distribution. I would like this distribution to look like the distribution of images or views that have been given. Okay, and the hope is that if I see enough of these views, the only way I can learn a good underlying representation is to get something that looks like the real distribution of 3D shapes. Okay, so the entire thing in picture, so we have this latent space Z, from which we'll first, given a Z, generate a 3D shape. Then we will use a bit of the Z to generate a viewpoint, and then render the 3D shape from that viewpoint. Okay, so we have a factorized generative model. So it generates images, so we can combine it with a discriminator that operates on images itself and backpropagate the loss all the way to train the generator. Okay, so that's, we call it PrGAN because it's a GAN with a projection module. So here's some examples of what it learned. So they input these binary silhouettes, and on the right, on the top are the 3D models that it generates. So there's sort of, you can see the shapes have some 3D structure. What's nice is the model learns to generate these 3D shapes in a canonical pose and renders them from different viewpoints. So you get some implicit viewpoint and part correspondences across objects. So there was an earlier talk today about learning symmetries, and there was a question that came up, which was on how do we impose symmetries in 3D? And one thought is perhaps these graphics engines and differentiable renders can let you combine aspects of view-based learning and symmetries that are explicit in the 3D data. On the right is a generative model obtained by projecting these 3D shapes onto binary images. And it turns out it's actually quite hard to learn a 2D GAN on images, and instead the 3D GAN plus projection module is a better 2D GAN. All right, so here's bases, which are symmetric, but the model doesn't know that. But once you train it from lots of data, it learns to imagine these kinds of shapes from different viewpoints. Okay. So the model doesn't have a notion of categories. So you can mix viewpoint objects from different categories together and throw them into the same generative model. And these are the 3D shapes it learns to generate. Okay, so now the airplanes are inverted because that's the best way to share parameters for generating motorcycles and cars and so on. Okay, so the quality of the shapes aren't that great, but this is one of the limitations of GANs in particular, but also that our supervision is very limited. So in some recent work, we've tried to improve it. So the kinds of things that are easy to label on images are things like depth or part segmentation. So suppose you had a set of projections where you could color the silhouette with different parts. So here we have the fuselage of the plane in pink, the wings in yellow. And if you're given a collection of these, you can imagine a volumetric representation where the voxels are also colored, and then project them to produce a colored image. Okay, so that's what's being illustrated here. But with these kinds of labels, it's much easier for the model to discover details. So now you can see that these planes have some structure like engines and the stabilizers and so on. So it's a comparison of the 3D discovered 3D representations from silhouettes at the very bottom with parts in the middle, and even using depth at the top. And what we found is sort of these part correspondence are just as powerful as explicit depth representations. So you're getting something like structure from motion, but being able to share the latent space across the shape categories. All right, so in summary, these kinds of projective methods can be combined with generative models, either GANs or implicit ones, to discover 3D structure. But the quality can be improved if you knew something about the viewpoints or have part annotations or have pose estimates. So these methods can be combined to improve results. Okay, all right. Then very quickly at the last part of our work, we want to infer a program that generates a shape. So the main motivation for an approach like this is we want a representation that's interpretable, perhaps editable, so that you can easily change it or apply it. So in particular, we're going to look at constructive solid geometry, where these programs represent instructions such as create an object, intersect with another object, and apply these kinds of Boolean operations in order to generate shapes. This kind of programs are popular for manufacturing parts and so on. Okay, so here's an example. So here's a constructive 2D geometry. So given a shape, we would like to write down a program like this, which is represented by the sparse tree here. And a compiler can take this program and perform these instructions and output a final rendered output. Okay. So the process in our image, X goes to Y. The T here is now a CSG engine, a compiler. Okay. And the space of programs can be described by these set of rules or grammar. So here, each shape is either a primitive or a Boolean operation applied to two shapes. Okay. So that can generate lots of different kinds of shapes. You can do this in 3D, where the primitives are now 3D primitives. And here on the right is an example that has many such primitives compiled together. Okay. So one of the challenges in these kinds of problems is how do we train these models that take inputs and produce outputs without having access to lots and lots of labels. So if you had labels, you could train CNN combined with a recurrent model to produce these programs as a set of steps. Okay, you need something that can deal with variable length programs and so on. So RNNs are a good choice. But if you did not have labels, you could run the program and produce an output and minimize some sort of a reconstruction error. So it turns out there is an additional challenge. So even if your renderer was differentiable, so you can implement CSG in PyTorch and make all of this end-to-end differentiable, but because the space of programs is discrete, you still need some sampling-based method to train these kinds of RNN parameters. So you use something like policy gradients, reinforce like algorithms to do this. Okay. So again, in pictures, we have a CNN that encodes the image and a recurrent model that spits out a program instruction in each time step till you reach a stop symbol. You have a CSG engine that compiles the program, produces the shape, and then you train it using reinforce. Okay. All right. So it turns out it's actually relatively hard to train these kinds of models. So the model initially does not produce any grammatical programs, so the compiler fails to run it. So instead, we found it useful to pre-train this model in lots and lots of synthetic data where we have supervised labels. So the CNN RNN learns to encode the space of grammar. And then we would like to train these models on real images. So we use policy gradients to fine-tune the network parameters on real domains. So maybe logos or CAD shapes. So just as some sanity check experiments, so we can generate lots and lots of synthetic examples. You might wonder if this model is doing anything better than, let's say, nearest neighbor. And here's a comparison of nearest neighbor examples retrieved for a given shape and what the CNN RNN generates using beam search. Okay, so that we're looking at top 10 examples. So it turns out the diversity and the combinatorial nature of the space, there are lots of shapes which just nearest neighbor examples aren't close enough. So the method doesn't do very well in terms of chamfer distance, whereas the CSGNet can often find good reconstructions, and often the nearest examples look semantically closer. If I don't have an explicit quantitative way of saying it, but visually they do look much more reasonable. So here are some examples on these logo images, which what you're seeing are inputs, and on the output are the reconstructions made by the algorithm, and the program is shown in the bottom where you have these different primitives and they're combined using different binary operations, not shown, to reconstruct the image. And it also turns out that the CSGNet is a better primitive detector than an object detection algorithm like FastStar CNN by a little bit. And it turns out this is mainly to do with how these models reason about occlusions and overlaps. So in object detection, there is a difficult step, which is non-max suppression, which can often delete overlapping objects and so on. And because CSGNet reasons about these kinds of things explicitly, it tends to do a lot better in terms of detection, and it's also a little bit faster. All right. So with that, let me sum up. So I talked about 3 different papers which were in the space of solving inverse problems without necessarily having tons of supervision to train the inverse model directly. And we combine ideas from implicit shape representations and differentiable graphics engines or rendering processes to train these kinds of models. And But I'd like to thank Matthias and Gopal, who are the students leading much of the work. And thank you for having me here. Right?